Bismillahirrahmanirrahim. Assalamu alaikum, students. In last lecture, we discussed the idea of relative motion. But today, I'm going to discuss another important topic. Topic is conservation of energy. Conservation of energy in a system of particles. So follow me, be attentive, and listen carefully. So our topic today is conservation of energy in a system of particles. Actually, as you know, we have entered unit second, which is about spatial theory of relativity. I am making the environment for studying spatial theory of relativity. So first I discussed relative motion. Now I am going to discuss another topic, conservation of energy in a system of particles. So what I'm trying to do, I'm trying to make the environment for spatial theory of relativity, right? So let us go into today's topic. You know, when an object interacts with one or more objects in its environment, we are free to define our system to be as many or as few of the objects as we choose. So, for any definition of the system, conservation of energy holds as long as we're careful about keeping track of energies within the system and energy transfers between the system and its surroundings. Right? So let us consider a system. So let there be some system. So it's my system, right? Now this system, let me make it bigger. So let there be some system. It's my system, right? It's enclosed by this boundary shown in black. So the system which is enclosed within the boundary, or let me show another line which I call system boundary, and another curve enclosing the system. So I call it system boundary. I call it figure 1. So in this figure, what I do, I am showing an arbitrary system around which I have drawn an imaginary closed curve which I call system boundary, right? Now the system inside the boundary has an energy. that may include many possible forms, some of which are indicated by K, U, and E, INT. What are these forms of energy? K indicates kinetic energy, U indicates potential energy, and EINT denotes the internal energy. K is kinetic energy, U is potential energy, E internal is simply the internal energy. Now here U refers to the potential energy that results from the interaction of the parts of the system among themselves. Interactions with the environment are represented not in terms of the changes of potential energies but in terms of external work W. So I show this arrow here. Let me use another color. This way. So this is here external work W. I repeat, I said U refers to the potential energy that results from the interaction of the parts of the system among themselves. Interactions with the environment are represented not in terms of the changes in potential energies, but in terms of this external work W, right? Now, the energy of the system within the boundary can be changed when external work W is done on the system by its environment as represented in this figure 1, right? Internal work done within the boundary by one part of the system acting on another does not change the total energy, although it may convert energy from one form to another, such as from potential to kinetic, right? So we can therefore write conservation of energy for the system as, let me use some other color. So we can write conservation of energy, conservation of energy for the system, for the system which we have shown in fig 1 as delta U plus delta K plus delta E internal is equal W. Let me encircle it. So I name this equation first. Now what is delta U? It is change in potential energy of the system. Delta K is change in kinetic energy of the system. And delta E internal is change in internal energy of the system. And W represents the total external work done by all the forces through which the environment acts on the system. I mentioned this first. W is what? The total external work done by all the forces, by all the forces through which the environment acts on the system, right? And remember the important sign convention for external work represented by W or shown in this figure 1. What is the sign convention which we use? Positive work done on the system, I write it sign convention for W. Sign convention is positive work done on the system, by the environment, by the environment tends to increase the energy of the system, tends to increase the energy of the system, right? And negative work done on the system by the environment, negative work done on the system, done on the system by the environment tends to decrease the energy of the system, right? And remember, negative work done on the system by the environment is also equivalent to positive work done on the environment by the system, right? You can think that way also. Now we want to illustrate these principles by considering block spring system. So let me draw figure. Let me bring my pen back first. What happened to my pen? Okay, I have got the pen. So it is simple. A table, right? On this table, I have a block, right? And that block is connected with a spring, right? So I write here description of the figure. I name it figure 2. Because we have already named one figure as figure 1. So I name it figure 2. So it's what? It is a block acted on by a spring. A block, and it slides on a table that exerts a frictional force. It is a block acted on by a spring, and it slides on a table that exerts a frictional force. So friction is present, right? And also, you know, the spring, if we have a spring and some mass is attached with it, if spring is in natural length, natural length means when spring is neither compressed nor stretched, right? At that moment, the spring is not going to exert any force on mass m. But if it is disturbed from its natural length, we can compress it, we can decrease its length compared to natural length by compressing it, or we can increase its length compared to natural length by stretching it. Then the spring will exert force on the mass m. You know that. Now in figure 2, what we assume that the spring is compressed from its relaxed length. So what we assume, let me use another color. We assume the that the spring is compressed from its natural length or relaxed length, right? In that situation, the spring is going to exert force on the block to the left, right? Now we consider this block as our system. I call it situation first. I have to actually consider 3 situations. I call it situation first. So in this situation first, what I do, I consider the block to be my system. So this block is my system. So in situation first, block is our system. So this curve shown in red is therefore my system boundary, right? So what are the energies which my system can have? K, kinetic energy, E, INT, internal energy. So my system can have is my kinetic energy of the system, that is block, and E, internal, is internal energy of the system. Now environment acts on the system through work. Now which work is here relevant, right? Now we assume the friction is present. There exists friction between block and table as it slides. So, and spring is also acting on the block. So there are two transfers of energy through the system boundary taking place. One is just show in the diagram first. One is I denoted by arrow, WS entering the system, and another is, let me use this color, another is WF leaving the system. What does that mean? So I'm saying there are two transfers of energy taking place through the system boundary. One is WS, positive conservative work, positive conservative work done on the block by the spring, by the spring, done on the block by the spring. Why we call it conservative work? Because spring force is conservative, right? And another is WF. What is WF? WF is negative non-conservative work, non-conservative work done on the block, done on the block, done on the block by friction, which exists between the block and the table. So for this system of our situation first, conservation of energy can be written as, so for this system, conservation of energy conservation of energy can be written as delta K plus delta E internal is equal to Ws plus Wf. I call it equation 2. This was my equation first for this arbitrary system shown in figure 1. So this is our equation second. I encircle it because this system possesses kinetic energy and internal energy. So kinetic energy can change, its internal energy can change because of Ws and Wf. So remember here change in potential energy is zero because the system within the boundary experiences no change in potential energy. The spring is not part of the system, so the spring potential energy is not considered. Instead, we account for the spring as a part of the environment through the conservative work Ws it does on the system, right? And note the directions of the arrows indicating the energy transfers in figure 2. I name it figure 2, right? So we are showing Ws entering and Wf leaving. They simply indicate our sign convention. Spring force does positive work, so it tends to increase the energy of the block, and friction does negative work, which tends to decrease the energy of the block. Now we use the same situation, but we change our system. So I take situation 2 now. This was my situation 1. Now situation second. Let me draw the figure again. So I have this table. Same table and same block on the table, connected by same spring, which we assume to be compressed from its natural or relaxed length, right? So we assume there is friction between the block and the table. But now what is different in situation second? In situation second, our system consists of the block and spring. So our system is now the block and spring. Remember in situation first, our system was block. Now we have added spring to block to make our new system. So in situation 2, our system is now the block and the spring. So we show the diagram like this. Let me use this color. So this is my system boundary now. So this is my system boundary. Now what are the possible energies in the system? Kinetic energy, block can have kinetic energy due to spring attached to it. Spring have also now potential energy, and you have E internal which is internal energy of the system, and there is now only one work, which is WF, which is negative, non-conservative work due to friction, right? Now, spring work doesn't exist anymore. Why? Because spring is now part of the system, and we have considered that in our potential energy term, right? So there is only frictional force as the external force that does work on the system. So for this system, conservation of energy is written as, we use this color, how we write conservation of energy for the system. Now we write delta U plus delta K plus delta E internal equal to WF. This is my third equation, and I answer to my equation, right? Now there can be change in the potential energy of the system, change in the kinetic energy of the system, and change in the internal energy of the system. And the source for all these changes, if we add all these changes, that will be equal to WF, right? So the energy of the system is now U plus K plus internal energy. Previously in the system, it was only just K plus internal energy, right? Now, transfers of energy between the spring and the block do not change energy of the system in this case, because the spring force is an internal force now that can transfer energy within the system from one form to another, that is potential to kinetic, but it cannot change the total energy of the system. Only negative frictional work by the horizontal surface can decrease the energy of the system, right? Now we take situation 3 now. Situation 3. I'll draw the figure first. Again, I have a table. And on that table, I have a block. That block is connected with spring, which is assumed to be compressed from its natural length, right? Now in situation 3, the system includes the table. So our system is block plus spring plus table. In situation 3, we include table in our system. So my system boundary is now this way. This is my system boundary, right? So our system is block plus spring plus table. What are the possible energies? K, internal energy, potential energy, right? The frictional force is now an internal force and contributes to the internal energy of the system, right? So in this system, which comprises of block, spring, and the table. In situation second, table was not part of the system, only we had block and spring, and in situation first, only block was our system. In situation three, now a system is block plus spring plus table. Three kinds of energies can have internal kinetic and potential energy, right? Now, how can we write now conservation of energy for the system? Simple, same as equation 3, but we have to put WF equals 0, right? As there is no external force, conservative or non-conservative in situation 3, which is responsible for energy transfers that penetrate the system boundary. So external work is 0. So for this system, conservation of energy is written as delta U plus delta K plus delta E internal equals 0. So this is our fourth equation. Let me encircle my figure for my equation, right? Now the frictional force is an internal force. In this situation, along with the spring force, energy can be transferred within the system from the mechanical energy, U plus K is called mechanical energy, of the block plus spring to the internal energy of the block plus stable, but the total energy, that's mechanical plus internal, remains constant, right? So this equation 1, which we wrote, this one, for an arbitrary system is actually generalized law of conservation of energy, which we illustrated using our block spring table example. So how can we now state equation 1? So I write equation 1, which I repeat here, that is delta U plus delta K plus delta E internal equal to W, my equation 1, this one, right? Is generalized law of conservation of energy, is generalized law of conservation of energy. It can be stated as, can be stated as, this generalized law of conservation of energy can be stated as energy can energy can be transformed from one kind to another in an isolated system, but it cannot be created or destroyed. The total energy of the system remains constant. I repeat, energy can be transformed from one kind to another in an isolated system, but it cannot be created or destroyed. The total energy of the system remains constant. By isolated, written here, isolated, it is meant that no external work, conservative or non conservative, is done on the system. So, this statement of the conservation of energy is a generalization from our experience and so far not contradicted by any laboratory experiment or observation in nature, right? Now, we will do a sample problem to understand it together. Sample problem. What does this say? A baseball of mass m equal to 0.143 kilogram is dropped from the top of the series tower. Let me write it clearly. Series tower at a height h of 443 meter. The ball reaches a terminal speed v of 42 meter per second. Find the change in the internal energy of the ball and the surrounding air during the fall to the surface of the earth. I repeat the question. A baseball of mass m equal to 0.143 kilogram is dropped from the top of the series tower at a height h of 443 meter. The ball reaches a terminal speed v of 42 meter per second. Find the change in the internal energy of the ball and the surrounding air during the fall, to the surface of the earth. Now let us move to the solution. Let me use another page for solution. Or let us start here, but use another color. This one. So solution. First we have to decide about our system. So let us regard the system as the baseball, the air through which it falls, and the earth. So we regard the system as the baseball, the air through which it falls, the air through which it falls, and the earth. And the earth. No external force acts on the system. The gravitational pull of the earth on the ball and the drag force of the air on the ball are internal forces in the system as we have defined our system. Now, the change in potential energy of the system is the change in potential energy of the system is delta U equal to UF minus UI, which is 0 minus mgh. G is acceleration due to gravity, m is mass of the baseball, and h is its height. So it drops from certain height, so it loses potential energy. Right? So substituting the values, you have minus, because potential energy decreases, 0.143 kilogram times the value of acceleration due to gravity. We take 9.8 meter per second square times the height is 443 3 meters. When you solve it, it is minus 621 joule. So potential energy of the system decreases by this amount, 621 joule. The change in kinetic energy, the change in kinetic energy during the fall is delta K Kf minus Ki, final kinetic energy minus initial kinetic energy. Ball is dropped, that means it starts from rest, its initial kinetic energy is 0, and its final kinetic energy is half mv square, where v is its terminal speed. When we substitute the values, what we get, it is half times mass, which is 0.143 kg. Then your speed, which is given as 42 meter per second square. You have to square that. It is, when you solve it, you can check it. It turns out to be equal to 126 joules. The kinetic energy of the system increases by 126 joules. Third part is internal energy. Remember, our system is isolated, so conservation of energy will be written as delta K plus delta U plus delta E. Internal is 0. That means delta E internal, that is change in internal energy of the system, is minus delta U minus delta K. And when we substitute the values, minus is because of the formula, and delta U is minus 621 joules, then you have minus 126 joules delta K. So when you solve, it will be a minus times minus plus 621 minus 126 joules. It will be 495 joules. So this is, first encircle it. So internal energy of the system increases by an amount 495 joules, right? And remember, we are neglecting the motion of Earth under the gravitational attraction of the ball, because when ball falls, Earth will be also pulled towards ball. We're neglecting that, right? So the internal energy increase is 495 joules. This increase might be observed as a temperature rise of the ball and the surrounding air, or perhaps as kinetic energy of the air left in the wake of the falling ball, right? So this was our solution. I think I will give you a homework problem. Let me give you homework. So homework is a question. It goes like this. A 4.5 kg block is thrust up a 30-degree incline with an with an initial speed of v of 5 meter per second. It is found to travel a distance d equal to 1.5 meter up the plane as as its speed gradually decreases to zero. Gradually decreases to zero. Part A. How much mechanical energy does the block lose in this process due to friction? Part B. The block then slides the block then slides from from rest back down the plane, assuming this color, assuming friction to produce the same loss in mechanical energy during the downward journey, during the downward journey. What is the speed of the block as it passes through its initial location? Let me repeat the question. A 4.5 kg block is thrust up a 30-degree incline with an initial speed v of 5 meter per second. It is found to travel a distance d equal to 1.5 meter up the plane as its speed gradually decreases to zero. Part A: how much mechanical energy does the block lose in this process due to friction? Part B says the block then slides from back down rest back down the plane, assuming friction to produce the same loss in mechanical energy during the downward journey. What is the speed of the block as it passes through its initial location? So this is all for today. Do your homework, don't waste your time. Make a notebook of these video lectures, learn at your own pace, and do not forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.